So one of the things that I learned firstly from Tish is that non-centralized intelligence, right? In biology, if you look at the plant animal kingdom, not always the evolution path has supported a centralized brain system for complex maneuver. In such cases, the biology forced body parts to be training, working, coordinating, and then you can see many things can be done. So these are basically non-centralized intelligence, or simply put, it's a morphology-assisted intelligence. For example, caterpillar. Caterpillar can move. Many people can actually think that how caterpillar can move. It's not from the centralized brain intelligence, but it's a kind of body part. It's basically the muscular contraction and then relaxation would actually create a vector forward while creating a tension, like a loop, like a rubber band, stretch and combine. So that's actually Trish taught me. And also this one, I've been looking very actively over the last like 15, 20 years, and this is actually something to me like more like a original thinking, that non-centralized intelligence. So to you, Trish, without any further ado. Yeah.
Right. Thank you, Chandra. So as he said, this is about intelligence beyond the brain, in the body and in the world around us, and it's very ghostly. So this is a story. This is not like a textbook or anything. So this is a storybook telling the story of my journey about maybe about 25 years of research into embodied intelligence. And I was looking for a good name, and then I picked ghost circuits because it's very ghostly. And partly because like I took about 5 years to write this book, giving up at least 10 times because I found it very difficult to stitch together all the pieces of information into one coherent story, and that is why it took such a long time. And luckily in 2024 I had a sabbatical, and then that was a good refreshing time to sit down and think deeply about the things I wanted to talk about. And then finally I thought, okay, let's put it ghost circuits. So things start to happen when you are hit by a brick, right? So this is when I was in Sri Lanka, like in 2003, after my postdoc at Johns Hopkins, I went back to Sri Lanka because there was a ceasefire between the rebels and the government. So I thought like I can do something to clear landmines in the north battle affected regions. There were about like 3 million or more landmines, anti-personnel landmines, and then the whole purpose was to bring those farmers displaced by the war back to the farmlands, and then like you had to clear the landmines. And then there are various ways to do that, a military approach to do that and a humanitarian approach to do that, right? So I picked the humanitarian approach, and then I went to this landmine fields, and then this is this is me, second from the right. Like wearing an anti-bomb like a gear, and then face cover, all that, but like I was shaking, right? So I still remember the fear I felt right next to a landmine, right? So I don't know whether there's landmine or if it explodes. They said like, okay, you will break your legs, but like some body parts will remain. So, but I was so scared, and I really wanted to get that person who is spending at least 8 hours a day looking for landmines from that site. Like, so that is, and then I watched how animals move around in those minefields. So I spent days and days watching what kind of animals are moving around, and then I saw like these reptiles, like so iguanas, like these are tropical reptiles that walked on these minefields without triggering any bombs, any landmines. So I wanted to study how the gait patterns, and then how they walk around without triggering landmines. And then we went back to the labs in Colombo, in the University of Moratuwa, and then we developed a robot. But this robot was different. So I wanted any developing country to be able to make this robot out of bicycle spare parts. So, and then I asked my team, okay, let's design a robot that can be made out of bicycle spare parts and any motors you can kind of salvage from junkyards, right? So our motor was a car wiper motor, and all the bearings you could buy from a bicycle repair shop. And then all this like metal were coming from mud guards and then like scavenged material purposely done. And then we designed that, but still we put a lot of effort into that iguana type walking in a minefield. But still then I felt that there's something missing, and I didn't know what was missing. Our robot got like entangled in vines, and then the iguanas were just moving through those like vegetation and vines with much elegance. And then like we developed our control algorithms, all the legs and everything, but it was nowhere close to a iguana, right? So it completely like shocked me, right? And then like we thought like, okay, we have PhDs in robotics, and I had the best I could find in Sri Lanka, but still there's this yawning gap. And then that completely stopped me and opened my eyes to something I thought was very fundamentally missing in robotics. So then I kept thinking about my background. So I was trained in Japan in robotics, and then like I went beyond my memories about the lab to cultural memories, right? So like so in Japan there is a festival, annual festival called Koi Matsuri, right? So this is like this fish who can swim against a flowing stream, and then when a child is born, they go and hang a koi like a kite on top of the river. So this is like lines, and then they put this koi, and then they celebrate that Koi Matsuri to give strength to the child, or wishing strength to the child, because this fish can go against a stream of water. And then very recently, George Loder's lab at Harvard studied this phenomenon, and then this is a dead fish, but this belly up when there's still water, but when there's flowing water, the fish dead body starts to swim against the stream of water, right? So this was like very kind of shocking, like how is this happening? And then there were various explanations, and then my explanation to this is that there is a mechanical program that starts to run when there is turbulent water and the fish, even if it is dead, and then that mechanical program is distributed, right? So a piece of the program is in the fish body, and then the other pieces of the program are in the turbulent water. When they come together, they complete the mechanical program and starts to run on its own, and then that run in a meaningful way to push the fish body forward. So you can see from basic hydrodynamic fluid mechanics, so if there is the stream of water which is turbulent beyond a certain Reynolds number, so if the fish face has that like basically wedge shape, it will have some vortex shedding or separation, and then this separation causes the fish, because of the water has inertia, it wants to swirl back in the direction, right? It was separated, and then it swirls back and hits the body in the opposite direction of the flow, right? And then that creates a tangential force against the original flow of water, and then that keeps pushing the fish forward. And then but is it enough? I mean, it seems to be enough to push it forward, right? But so now,
normally the fish should go backwards.
A stick would go backward, or a ribbon would go backward, but the fish goes forward, right? So, and then this is subject to conditions. The conditions are the fish should have the right shape of the face, and then right like slipperiness on the surface, right. So, it cannot be too rough, otherwise vortex shading will be high frequency shading. And then it should have the stiffness distribution from the head to tail, a level of softness that will resonate with the turbulent frequencies of the water, right. And then that will have a positive feedback loop that keeps amplifying these vortices in its own advantage. And then let us say if the fish was frozen and you put it there, the stiffness is gone, it is gone. So, I call it ghostly because it, when the conditions are satisfied, the program kick starts itself, and then when the conditions disappear or no longer there, this dissolves, it disappears, right. So, it is ghostly because you cannot say where the program is, right. It is everywhere and it is there, right. So, this was my initial thinking of a ghostly behavior of intelligence, which is distributed and then but they come together to do meaningful functions when conditions are right. Okay, let us go back to a little bit of our history. So, about before the Cambrian explosion, which was 520 to 540 million years ago, about 550 to 600, even 700 million years ago, we had these like jellyfish type like primitive animals floating in the seas, and then these corals, right. I mean basically they are trees, but like you cannot say whether it is a tree or an animal because they have actuators, they move around and then they just do some active perturbations. So, this jelly you do not know where the brain is, there is no eyes, there are no like nothing actually, they just float around, but like so they had contractile fibers that first appeared about 600 million years ago. So, they show that sophisticated behavior can emerge with little centralized control, right. So, there is nothing centralized, like you can see it is very random in its actuation, and then they float around, there is no communication. And then even corals, like it is pretty random, nothing repeats. So, these movements somehow appeared about 600 to 700 million years ago, and there is no vision. There is no vision. There may be some primitive form of tactile sensing, but a surprising thing happened in the Cambrian explosion, which was about 520 million years to 540. Within those 20 million years, a massive diversity of species came. That is why we call it Cambrian explosion. And then in that, the marked thing in this period was the appearance of vision and hard formations, right. So, predator prey dynamics, and then because they had this predator prey dynamics of the vision, they formed vertebra, so skeletons basically. So, they wanted more like structures, like jellyfish cannot like grasp something and then kill something or like anything strong, and then you need like bones to do that, right. So, they developed bones and then vertebra and at the same time vision. So, this created a massive difference, and then people like animals were competing against each other, preying on each other, and then they grew in size because of this competition, right. I mean all the way up to the dinosaurs, right. So, it was a massive explosion. So, in that, like so if you look at like slow down a little bit and then look at how the formation of ice, the photosensitive cells appeared before the contractile cells about 700 to 80 million years ago, these photosensitive cells appeared. And then this jelly-type contractile tissue, which were very transparent tissue, appeared about 550 million years. And then the Cambrian explosion came, and then we had the eye. Now, there's something very ghostly here, right? So just imagine this part is that you can contract and expand a lens, right? So cornea is like a jellyfish, right? And then so this part is photosensitive. Those are coming from the photosensitive cells. And then this is a collaboration of different species, this eye, right? This eye, inside that eye are primitive species collaborating as a circuit, right? So they form a circuit so that now in that collaboration you suddenly get vision, a perception, and then they stay there like that, right? So this building blocks was very amazing. So this is the pupil, right? So of your eye, constricted and dilated, and then for me this is pretty much a jellyfish, right? Okay, so these things keep building up these circuits is a continuous drive from the single cellular amoeba to multicellular structures, and then the drive behind this multicellularity is to do better things and pursue more and more by collaborating, right? So it's basically a swarm. And then to theorize these things, Darwin in 1859, so when he wrote the origin of species in Galapagos Island, he observed most of his observations, and then he wrote this book. And then in that book he said three things actually. Variation exists, I mean after Cambrian explosion, of course, and then there's a species, same species has variation, like you take a reptile and then they have slight variations, and even birds have slight variations in their beaks and then colors and everything in the same species, and then some variations are inherited, like so they pass from one generation to another. And then natural selection acts on inherited variation, and then maybe the birds with a slightly longer beak can maybe drill into things more than the other birds, and then they eat more and then they survive more. Various environmental factors. So what happens now is, with this variation in the species, the way they get coupled with the environmental factors, basically how they establish Gauss circuits are going to be different. As I said, in that fish, the Gauss circuit depends on the conditions, right? So the parameters in the body and in the environment, right? The turbulent water, the turbulence level, the frequencies, and then the fish body, the stiffness and the shape matter. When they come together, the program completes, and then that means by having slight variations in your side of the story, then you might be able to couple with factors in the environment that other species or other animals in the same species cannot, and then that can give you competitive advantage. So let's say one fish can really swim upstream with little effort because a slight difference in the angle of the face, right? And then that fish might survive than the other same fellow fish in the same family. So Darwin didn't go beyond that, right? Because that is what he could say with what he knew in 1859. And then these ideas of epigenetic memory came. That was very interesting, especially in 1900 and from 2000 onwards. So people found that the Conrad was key in 1942 to say this epigenetics roughly the same time DNA was shown to carry genetic information. So mostly after the Dutch famine, people found, like in the Second World War, most work were after the Dutch famine. So they found that your genetic code is like a piano, right? So you have the keys, but the sound depends on how somebody plays it, right? Then they found, okay, so there is this genes and then folded, and then there's epigenetic code that tells how this genetic code to express, right? So let's say if my stem cells goes to the skin, and then these cells can express a skin, and then if it is in the bone, it can express as a bone. That is the genetic expression. But this note-taking genes called the epigenes that are not really expressing but telling the other genes to express. And then this epigenetic code can keep a note about what happened in your life. And then that can pass that story about your life to your children, and then it might influence the way your children express their genes. So this idea was very powerful, right? So like for example, there's this, you can do an experiment, you get a plant, and then you dehydrate that, stress that, like simulating a famine, for example, and then you recover that somehow. You don't let it die, and then you water at some point, and then it keeps this memory of that trauma in its memory, and then it asks the genes to express in a different way in the subsequent generations if there is sunlight or too much drought. Maybe it grows their roots deeper, right? And then it can have a bigger leaf, or leaf shedding can be a little different, and then their behavior changes differently, which Darwin didn't know, right? Like people get this very confused. Darwin's theory never said about any kind of epigenetic expression. He only said survival of the fittest, of the variation, and then he didn't say anything about transferring information from one generation to the other. Of course, he said in pangenesis, he kind of indicated, like he had the hunch that this happens in his, though he didn't know epigenetics, like so in his pangenesis theory, he kind of indicated that information from tissues could be somehow influence the future generations, right? So he didn't say. So one of my PhD students, Saina Akon, in 2018, her PhD was about this, right? So she asked this question. So you see these monkeys sometimes doing like brief episodes of bipedalism when they especially carry food or a rock like the stone to crush these nuts. And then the question is whether those brief episodes of bipedalism can carry some information about bipedalism into the subsequent. So we cannot wait for a long time to do this. And then the hypothesis is, okay, our Homo sapiens, sapiens, and Neanderthals had this bipedalism evolving from this food-carrying behavior, right? So and then reaching out behaviors. So she took an inverted pendulum to simulate a bipedal body, and then asked a controller to somehow stabilize that by pushing and pulling, right? So when the pendulum is like that, if it falls this way, you should push it this way to get it balanced, right? So and then when the important thing is, so when you get the controller to push and pull and somehow balance it, it informs this joint about something it is missing, right? So when you like for example, if it is forced this way, right, and then if you push the cart that way, it tells this joint that you need a spring, right? So say you had a spring, so then when it tilts, the spring will push it back, right? Pull it back. But because there's no spring, you have to implement that spring by pushing the base this way, right? And then her PhD was about distilling down morphological missing pieces by looking at how the brain is trying to control the body to compensate for the missing pieces. Okay, and then she published her work, and then surprisingly, so she asked this joint to grow a spring and a damper, and then the brain, which is the controller, didn't know that a joint is learning to grow a damper and a spring, and then somehow when the spring was grown, the controller withdrew from its function, so it relaxed its actions. And then both of them settled down to a kind of a autonomous, like like a settlement, this did not keep growing the spring, right? And it stopped somewhere, it converged somewhere, and then this settled down, and then they settled to a minimum energy solution that we didn't ask it to do, right? So this was the fascinating thing about this. Like, so this was the first, I guess is the robotic theory to explain how the brain's attempt to control our body could inform the epigenetic memory to express genes in a different way, to grow bodily parts, which are like ligaments and muscles. Okay, so let's go back to our ancient history, right? So, like this Toji temple is in Kyoto, in Japan, and this temple, this pagoda, has how many stories? 1, 2, 3, 4, 5. I think it is said like there's some concealed 2 layers, 7 stories. That survived 400 years of Japanese earthquakes, right? And then it never broke down for all the earthquakes. And then architectural historians looked at it, and then they saw that each layer is independent, and then they are free to slide. So you see these like holding bars, and then the sliding bars. And then when there's an earthquake, it behaves like a snake. So you have that inverted pendulum, right? So I showed you. And then when there's an earthquake, the bottom shakes, it can shake, and then the top has inertia, and it can stay, right? So in a normal building, if it is rigid, when the whole base shakes, everything has to shake and then oscillate, and then that cracks the building, and then this building doesn't. So what does it mean is the ancient designers, the ancient architects, knew something about this. They didn't call it ghosts, I guess. They so that we can mechanically program things into structures that will autonomously boot themselves into programs when there are environmental conditions, right? So they're like an earthquake. And then this earthquake, once the earthquake is gone, always this building settles down to a straight, rigid structure. It's like you have a ball in a basin, and you can shake the basin, and the ball will wobble, right? If you have a curvature, always when the basin stops, the ball will settle down at the center. So they built in these potential functions is slight curvatures in each sliding surface, so that there's a minimum potential they will settle down, right, after the earthquake is gone. So this is an example of a mechanical program you can program into a inanimate building without a single sensor, no computer, nothing, right? So it stays there dormant forever, waiting for the conditions to rise, and it will kickstart that program and run. And then, like the fish swimming upstream, this building survives the earthquake, right? So it's a program. So I will go to another philosophical side of the Buddhist philosophical idea of anatta to now bring you a little closer to this idea of consciousness. So what it says is there is this intentional action. Every intentional action reorganizes your mental and bodily formations. You cannot do anything intentional without leaving a trace in your mind or the body, right? So it leaves a trace in your mind or the body whenever you do any intentional action, right? And then these formations, bias projections of awareness on sensory experience, called vijnana, right? So it's the Buddhist notion of consciousness. Okay, view it this way. If you look at the empty space, it is always dark, right? It's always dark. But when the moon passes above you, it shines, right? So when that means the empty space always had the light you didn't see because there's no object to shine on. So when an object passes, a planet and its moon, then it shines. Then you know, oops, sorry. Then you know there was awareness in that, oh, there was light in the dark space, right? So the Buddhist notion of consciousness is about all of us has a still field of awareness, right, that we don't see till a sensory experience arises. So the sensory experience shines on that awareness, and then that sensory experience creates two phantoms, right? One phantom is the object, and then the other projection is a sense of me, a feeling of me, right? Like what we don't know is that that phantom projection of a self is relative to the sensory experience, right? Let's say you go in front of your mother or the father, you feel like a child, right? Me, the child, and then you are here, right? Whatever you are thinking who you are is relative to this context, this sensory experience, right? Maybe a student, maybe an intellectually, like very curious person, right? Because of this, discussion happening, or a person at Imperial because you are at Imperial. Like everything is like whatever your projection as who you are is relative to the sensory experience, and then consciousness therefore is always a differentiated perception of this and that. Okay, so that is the idea. Consciousness is a differentiated form of awareness with a phantom of that and a phantom of me relative to that. So anatta is the most important idea. Anatta is a process of arising and passing of consciousness, is driven by causes and conditions without a central arbitrator. So it says like there's no central determining force or a controller that drives everything. It is just rising and passing away on their own, given conditions and the causes and conditions, and it is everything happens at the same time. So the Buddhist notion of causation is not a chronological causation. So it is like, okay, that happened, then that is why this happened. It says like, no, if that is there, this is there at the same time, right? So it is like a perception of me and a perception of the world, which is called the consciousness. And then that consciousness is not a given thing. It totally passes away when you move from place to place, right? You look at your friend, you suddenly feel like I'm a friend. And then you look at your parents, you suddenly feel like a child, and like your loved ones, or it's like boyfriend, girlfriend. It's totally different. Like instantly, it can change, right? That perception. And the other thing is the bodily formations. This is the mental formation, which is the consciousness, and then the bodily formations totally depends on what you do, right? So let's say this is me in a karate, like a kumite, and then the feeling of me depends on this person, and then what I could do at that moment depends on what kind of exercises I have been doing for the last 20 years of my practice, right? And then which can be very different from a ballet dancer, right? So they have done their exercises for so many years that lets them do that, and I cannot do that, right? And then there may be a cricket player. So you have to consciously do that's called karma in Buddhism, and then like whatever you can say, it is bodily formations intentionally done. So, but there can be some bodily formation that can transfer. For example, Bruce Lee is like an amazing philosopher of martial arts, and then he was a champion in cha-cha. So he is a dancing champion. And then that dancing, he said, is not very different from when he is in doing kumite in martial arts, and then that has transfer effect, right? So, for example, when you do squash and then you can do tennis, maybe that has transfer effect, right? So similar things, like it is not just one-on-one. And then a very important thing he said was all learning begins with adding to your knowledge, adding to your awareness of different possibilities. But the height of cultivation comes when you move beyond this point and begin simplifying and hacking away the inessentials. So basically, our ghostly these formations and evolution is a divergent and convergent process, right? So you add things and diverge, and then you kind of delete things or merge things, and then you converge, right? So that is pretty in the design world. So this is my colleague Silke Grabinger. So she is in Austria, Vienna. I met her last week during ICRA, and then she gave me this paper she wrote. And this interesting thing about, like, she's an arts performer, and then she performs with robots, and then she has this interesting theory of the triad. So in the abstract, she says the article explores the intersection of creative robotics and the performing arts, and the purpose in new conceptual framework of the human-robot recipient triangle. In the human-robot recipient triangle, it is inspired by Jacques Lacan's theory of desire, which examines how the subject, fragmented and incomplete, that the subject seeks wholeness through unattainable desired object, right? So HOR triangle interrogates this fundamental contradiction of anthropomorphic reactions with robots. Performers and audiences attribute human-like qualities to robotic entities, desire their lack of consciousness or intentionality, while the recipient's observations introduces additional layer of interpretation. So this triadic interaction, so the human and the robot and you as the observer, so whatever the observer, as an observer you feel about this, totally is a creation, it's a fabrication in your mind, right, depending on your history and then the constructs you have, right. There's nothing there or in her, right. So according to Lacan, the subject, i.e. the human, is not a pre-existing unified entity, but rather a fragmented product of the interplay between the subject's relationship to an object. So that means, like, you listening to me is being created right now, okay. So and the way you get created right now depends on some historical, like, baggage you brought here, like your knowledge, and then like some thoughts you had, and it interacts with my talk, and then you get created right now as some kind of a phantom, and then it is not something like fixed. It's very ghostly. Okay, so let's do a little experiment. So can you look at this, and then if you have a mobile phone, go to menti.com and then enter this number 31374030, and then explain this scene in maximum 2 words. I'll go to Menti. Do you see the question? Give me a second. So I will. The number is 31374030. So I'll put it back. Do you see this number? 31374030. Okay, so let's see show responses. Serene, Japanese garden, peace, zen, entering nature, garden view, calm, green. See how you are created by the scene, right? So the scene creates you in these diverse ways, right? So whatever 19, 23 different people were created in different ways. Did you get the point? So the same scene, there's nothing called a scene, how you were created right now by the scene is different, and then they can hang around something, and then this is the burden of the artist. So the artist can project themselves using robotic human interactions or music or arts in some kind of a sphere or a domain, and then you can keep the audience in some kind of a domain like that, hanging around some kind of a, let's say a sphere, but very different, right? Giving this thing. So this is this whole idea. Hope you got it. Okay. All right, let's continue. So this ghost circuit is because of this it is ghostly, right? There's nothing like a static deterministic way of creating that. So let's look at this example, right? So these are hex bugs. You know them. These are just rubber pieces, right? So there's nothing like no motors actuating them. This is me trying to do that, and then they just can bounce off the ground because there's a vibro actuator, and then because of the legs were pointing backwards, they can only bounce forward, right? Because it was made that way. And then there's this wedge-shaped face so that it can bounce off something. Because it's not thinking, there's no computing, there's no planning, no actuation, it can just bounce forward, and then if there are some rubble, it can get stuck, right? So there's nothing intelligent about it. Let's say if I then move around these pebbles in random patterns, random order, this is a shoebox, and then I did this at home, and then there's nothing sophisticated about this video. And if I release the same bug again, you might get some different feeling about the bug, right? So you might think, oh, this is now sensing or planning something or looking for something. It's totally your story, right? There's nothing. So this is the projection on you, your mind, and then there's nothing like you might think even this is intelligent or this has sensors, this has computing happening. None of that, right? So it is just bouncing off the ground because of the pebbles. The pebbles, their mechanical properties contribute something to the orchestration, your story, and then this yes, there's some mechanical thing about these bugs who can just bounce off the ground, and then together you cook up a story, and then you call it some kind of intelligent in the scene, but that total intelligent story is a cooked up story in your mind. Okay. And then when you put swarms of them, they can appear to be. So intelligence is nothing out there, it is in your mind, right? So you assign intelligence to a scene. Okay, if you didn't see that, this is just rubber pieces bouncing off rocks. So I call this a ghostly circuit because pieces or parts of this orchestration came from pebble that has no brain, nothing, no senses, right? These stones, and then parts of that came from this bouncing rubber piece, and then everything put together, it orchestrated, right? So that sense of intelligence. So you can weave it, if you go back to the dead fish example. So this is a dead trout just passively floating against a stream of water, and then you can see the ghostly circuit, which is like, let's say like we have some springs and network of springs, and then these are connected through some kind of nodes, and then imagine this spring is the fish, okay? And then do you agree that like by changing the stiffness of this spring, I can influence the entire network of springs, right? So just by changing one link, I can influence the entire, like a random stochastic behavior of the entire network. So the fish, when it is alive, this is a dead body. So this is, if it is alive, it could change its swimming behavior or the stiffness of the body to influence the entire behavior of the network, which is the turbulent water behavior, and then harness energy from that to swim against it, because from place to place, the frequency components of turbulence changes, and then it has to tune itself. So I call these two processes in the brain MCT and MCM type control. MC is for motor control, for motion, which is like swimming behavior, the wavy behavior, and then MCT is the motor commands for tuning the body, right? So the tuning, and then these two concurrently happen to help each other in any living being, right? So this was not kind of separated before, like I separate them. So for example, you are eating, let's say eating with fork and knife. So you might not notice that, like, so when you cut vegetables, the way you cut vegetables, and then the posture when you cut meat is different, right? So you change your posture slightly to interact with something. So that is tuning while cutting, right? So MCM is the cutting behavior, and the MCT is your tuning behavior, right? So tuning your stiffness and the posture. So both are important, like to recruit computational capacity in the dormant body. So for example, like the knee joint has a angle dependent damper. So when you have an angle dependent damper, that is a low pass filter, right? So but this low pass filter has a cutoff frequency that can be tuned, because by changing the angle of the knee joint, you change the viscosity of the joint, and then you move the cutoff frequency of the low pass filter. So but the brain is aware that the knee joint has a tunable low pass filter, right? So let's say you're riding a bicycle, and then the bicycle goes to a bumpy terrain. So one way is to, okay, you keep riding the bicycle seated, and then now the head shakes, and then now you have to do a lot of struggling, right, to keep balance and then like keep riding the bicycle. But the brain is smarter than that. The brain knows that there's a low pass filter in the knee joint that can do this job, and then I can tune it, and it gets your body to stand up and then ride the bicycle with bent knees, and then getting the low pass filter to filter out the high frequency components. So the brain can focus on now low pass information, low frequency information of riding the bicycle, and it enjoys that way, right? So the Gauss circuits are about continuously tuning your body, and at the same time influencing motion and force with the environment, and establishing these circuits and tuning them on the go. So a GP would do the same thing. When you go to a GP practice, they would examine your body, but like look at the tiny tuning they do. Like, so they sometimes stiffen their fingers, relax their fingers, like do unimanual control, bimanual examination, all those actions to feel something, a random variable in your body, right? So the organ conditions and things like that. So we can use this idea of Gauss circuits and do practical things. So this is a former master student called Thomas Gordon, and Ellen and Barry Mulvey, he's my PhD student. So they designed this transformable wheel, right? So this wheel, it behaves like a wheel on flat terrain, but the moment it hits an obstacle, it pulls out a tooth, a hook and then hooks on the obstacle. So the obstacle is no longer a problem now. It is part of the solution, right? It is just like that fish using the upstream, the stream of water to swim against it. So you can basically have a dormant program in your wheel, a dormant mechanical program in your wheel that can use the geometry of the obstacle as part of a solution, and then get it out. So this is some work we are doing with NASA Jet Propulsion Lab, especially for Artemis 3 mission, and this has made it so much more efficient, right? Because if you send a robot to a planet that we don't know, that's very difficult to do sensor based control. So you have to have mechanical intelligence in your robot that can autonomously respond to the local conditions, because we cannot model that distant planet surface. Right. So here, I go back to Bruce Lee. I admire him as a philosopher and a martial artist. So what he said, so all learning begins with adding to your knowledge, adding to your awareness of different possibilities. But the height of cultivation comes when we go beyond that and then simplify using merging and deleting, right? This is expansion and reduction that we do in design engineering, right? So in design engineering, so you always go with this double diamond approach, right? So first we try to understand the problem. What problem are we solving is a discovery process. And then how do you know what problem you are solving? You have to probe it, right, with your design solutions that are also diverging at the same time, right? They're concurrently happening by interfering with the problem and then illuminating different dimensions of the problem through your design interventions, and then we go converging and then converging to a solution, and then at the same time we understand the problem, what the problem is we are solving, right? So it is a concurrent process. It's like this, right? So let's say this cheese tray. So this cheese disc or whatever, the cheese is rolling so elegantly, and then people you can see, right? So they are not designed for that slope walking, right? They fall, they roll, they break their legs, but the cheese so calmly rolls, right? And then you can see this and then see, okay, so there's something about self-stabilization in that cheese disc, and then these forces come into being when a thing like a wheel rolls, right? And then these forces self-stabilize. Then why do you have to stabilize it? You just have to have the morphology of a wheel that can self-stabilize, right? And then you can then extend that. Okay, now let's get a wheel and then put a person on top of that, and then design a seat so that they can sit and then do the pedaling. As far as the wheel keeps rotating, the person will be stable, the wheel will be stable. All what you had to do is to keep spinning the wheel, right? So this is how design thinking diverges, right? So starts from something, and then by interfering with the wheel, you understand what the wheel is, and then you understand the heuristics of controlling a wheel, and then you can end up designing. You can converge to a bicycle or a motorcycle or a unicycle. Various options are there when you interact with the problem, right? Do we have 5 minutes? Maybe. I just wanted to give you an example of research of mountain goats, right? So how mountain goats survive on those cliffs. This was done by this Chris. So what Chris did was went to the Peak District and then did so much divergent thinking about, interfered with the problem of slopes by introducing this hypothesis, different hypotheses about what it means to be surviving on a cliff. And then they converged to a single piece hoof without ever touching a mountain goat. And then we understood that the hoof should have these features, right. So, we had divergent features like okay, compliance in this direction, compliance in the pitch, and then these sharp edges, and then the edges, sides of the edges in these shapes. But then we realized like actually we can combine these features to simple features and then finally end up converging, independently converging to a hoof that looks like a mountain goat hoof, right. And then not exactly like a mountain goat, but it can do the things the mountain goat hoof does, right. So, this is Chris climbing Peak District slopes. Actually, today he is in Peak District, so that is why he cannot. Vasco made a leg for him, a hoof leg for him, and then he is testing that. I have a few slides, but I will maybe stop here, and then I will go to Yukun's. This is Peiyu's work, which is continuing these ideas. Like so, this manipulator had this soft fingertips that solves the problem on its own without really thinking or planning about grasping objects, natural objects. So, this is Yukun's work again, like he got inspiration from this leaf that can go in one direction like that fish, and then he did a lot of divergent thinking about these origami structures, and then finally he came up with a capsule or a colonoscopic probe that can go and look for anomalous tissue in colons. This is a simulated colon. Yeah, so I will stop there and then maybe take some questions. Yeah.
Thanks, Trish. Excellent talk.
Thank you.
The floor is now open for questions.
Yeah.
Thank you for the talk. I find it very fascinating, especially bringing in the philosophy aspect to it. It clarified actually so many other aspects of design.
Thank you.
I'm thinking about prosthetic applications.
Mm.
The hand, for example, is applicable to many different things, grasping, holding, caressing, whatever. I wonder, because in all these examples they were for a very specific purpose. Like, for example, the wheel, climbing up the ledge, or the goat hoof, it's for going on slants. Is there any limit to the environmental complexity that an object can be coupled with? And how do we think about that limit? So, for example, the wheel probably, it doesn't go upside down.
Yeah.
That's an extreme example, but I'm wondering if there's a way to think about the limits of this morphological limitation.
Thank you very much. So that's really the core of the problem. Right? So there are limits. So the limits come from the conditions necessary to maintain the Gauss circuit. So in a mathematical sense, we call it metastable systems. So let's say the bicycle. So bicycle can keep stable given some conditions like the speed of the wheel rotation, and then the friction of the terrain, and then the bumpiness, and there's a limit to that. So you go beyond that, you feel that the bicycle is no longer stable at that speed. Either you have to reduce the speed, go slow, and then there is a limit to that too, right? So you have to you cannot go stop, and then you have to maintain some, and then at some point that is why we come off the bicycle and then start to walk. So this terrain is not there for my cycle, right? If it is too rocky, for example. So there are limits, right? And then how do you know that? So the Gauss circuit starts to dissolve, and then when it does. So it's a perception, or you can get that feeling. So what robots don't know how to do is they struggle till the end, till completely the thing collapses, and then they would try to ride the bicycle till they fall. But our brain would know, no, I have to now get down, right? So change strategy. So this is where a big problem lies. Right? So there are limits, and then how to know the limits is the question. Yeah.
Yeah.
Yes.
When you're designing an object, should you start off by thinking about the environment it's in or the object itself?
The challenge is we don't know what the environment is till we put the object in the environment. So it is like it's both get illuminated when they are together. So it's like turbulent flow without a fish is something, right? So it flows, and then the moment you put the fish in, both the fish changes and the turbulence changes, and then they come to a different formation, and then they become a coupled system that fish. So that is there's no disengaged or disembodied intelligence or dissituated. So it should be situated in the same context, and it should be embodied. So that's the difficulty. It's concurrent. Emergence is concurrent, and the object and the environment should be there. Andrew, yes.
Andrew.
Yeah.
Really interesting talk, thank you. I want to just dig into the philosophy aspect of this a little
Yeah.
bit more. So there's obviously a lot of affinity, I think, and probably a direct influence between some of this Buddhist philosophy and some of the more kind of relational ontology stuff that you get in maybe more contemporary Western
Yep.
philosophy, and things like Karen Barad and the like. I wondered about the position of human-centeredness in all this, because in the talk you said sort of two different things. On the one hand, you said, well, this idea that we are a subject, as a unified entity, isn't really true. It's all these different kind of elements that come together, and so kind of destabilizing the idea that our singular intentionality is always the center of the story. Absolutely, I'm more with that.
Yeah.
And then you also said, like, when we saw the little bugs running around,
Yeah.
it was essentially the human, us watching that,
Yes.
projected onto the bugs the idea that they were intentional agents of some
Yeah.
sort. So there somehow the human was the center of the story more than the little object. So I guess, where do you see the kind of human element sitting? Do you argue for a kind of more human intentional design stance, or do you argue that essentially humans are maybe only one part of a larger ecosystem when you're in the context of designing these sort of passive mechanical robotic systems?
Yeah. So it is actually going back to that triad of the object, observer, and this hypothetical, like this creation, right? So it is like, so whenever we have this the sensory stimulus, like it can be visual, it can be auditory, it can be anything, and then that the projection on awareness creates that like a elusive consciousness which is very transient, and then that creates that phantom me which is very transient, and then this is where the trick is. It is at that moment, like when we saw that scene, like different people interpreted that in different ways, like put different words to that, and then so it is very transient, and that's the like elusive subtle thing, and then it disappears completely, and that is why there's no agency or a self in that. That self is created at that time, and then it is very momentary. So this is the bit we struggle to really understand. So seems to be happening. So this is the kind of I would say open question about this book, like what is this really? Who are we? That question. So I don't have a very concrete answer, but I just wanted to leave it open for that. Right? So it's yes. Yeah.
So all these, So all these circuits, they have somehow evolved in the world naturally through the animals, and the best we can do as roboticists is get inspired from the mechanisms and build robots that have similar mechanisms. But what is the process of, and these mechanisms could be like different springs combinations or different links with different joints or something. But what's the process of designing a ghost circuit from scratch without any biological inspiration?
Yeah, this is about, like, so what we said, the divergent process. So you go to So we don't know the problem we are solving at the beginning, right? So to probe the problem, you have to probe it. So the only way to probe it is with the initial hypothesis of a design, right? So say like before the cup was invented, like so people, how were we drinking water? They go to a puddle and then have the hands, hands were their cup, and then they get the water, and then a design thinker might think, okay, so can we solve that problem, right? So what are they doing now? So they are making some kind of a cup, right? Can I make a shape something similar, and then see what the human would do with that, right? And then I don't think they knew about clay or anything so maybe they took some shell from the environment and then gave it to the people, and then, so how they use the shell, maybe and then they watch that, and then you understand the problem, right? And then the other dimensions start to appear, and then people may prefer some shell than the other. Why did they prefer that shell? Is it the color of the shell, the shell, the weight of the shell, or the appearance of the shell? It looks cool, whether the other, it is not just the functionality then, it is just the function and the form, and then you now illuminated different dimensions of the problem. So you kept iterating, and then we converged to these modern cups, and then there's no single cup. There are multiple designs, right? So there's no single solution to the design problem, because each cup can satisfy a certain set of dimensions to the problem, right? Color, yeah. Yeah.
Actually, that's good to ask my latest.
Yeah.
So it's a kind of maybe criticism personally myself to the robotics
Yeah.
community as well.
Yeah.
Do you think we kind of as a roboticist ignore adaptation or give less value to adaptation and put more on the intelligence? That's the first question.
Yeah.
And the second question is, we see from nature, we inspire from nature. I think also the same questions I saw, we are very human-centered, and we just observe and try to kind of copy the problem. For example, you showed the goat idea, how it climbs. What if we didn't have the goat? How are we gonna simulate something that we don't know to find the solutions or go over the bio-inspire?
Yeah.
I like to listen about that.
So so in my approach, I don't agree with bio-inspiration. I don't agree with biomimicry, because both are flawed, right? So biomimicry assumes that you know biology that we don't know, right? So the goat hoof is not what you see from outside, right? There are dynamics there you don't know. There are so many dormant, let's say that Toji Pagoda. You look at the Toji Pagoda, it's a building, right? You don't see the mechanical program dormant inside that can kickstart when there's an earthquake, right? So it is programmed into it, right? So the engineers, robotics engineers, make this mistake with the arrogant stand that we think we know. We know the biology. I know what inspiration I can get from biology, and it's there from the outer appearance, right? Which is a flawed thinking, and that doesn't work. That is why I take a different approach. I use the robot to probe or stimulate the problem, and then understand the problem at the same time. And it's a series of hypothesis testing that converges to a robotic solution, and then that converges to a understanding of what the problem is also. So I start with zero knowledge about what should be the solution, what is the problem, right? So I just go there. So it's contextual and then embedded in the situation, and then do that. So if I want to solve a medical problem, I sit with the clinician and then observe the clinician, what they are doing, and then things like the landmine detection. I straight away went to the landmines, risking myself, and then experienced that heat, the fear, everything. That is how I got to some solution. So robotic engineers make this mistake. They don't, I mean, not everybody, right? So prefer to sit down in front of a computer and then think that they know, and then they do things, but not really grounded. I don't like that
So
approach.
you believe kind of robotics might converge to a kind of a science branch that
Yeah, robotics and design thinking should be combined. That's why I think people who are graduating from this department have huge more value than a roboticist who will graduate from a conventional engineering department. So because we combine that situated design thinking with
So let's take a few more. Andrew, and then one over here, and then away. Yeah, Andrew.
Sorry to ask another one.
Yeah.
I'm really curious also about how your notion of embodied intelligence maybe, well, how it chimes in with other kind of 4E cognition theories and such. I'm thinking of things like enactivism, for example. And you give the example of the trout, and then that leads me to think, well, what about the live trout? And and more generally, in the bicycle riding example, what about the kind of way that embodied experience propagates upward, not just in what I think is actually probably a learned decision to actually stand up on your knees rather than something that a child would do when they first approach a bike.
Yeah.
But also the way that even our higher level kind of cognition that we think of as being so separate and so kind of machinic in nature, how is that influenced by the sort of ghost circuits? Because I don't think those things are entirely separate either.
Yeah, exactly. So it's just it's this knowledge that emerges in the ghost circuit. So it's itself. Right? So when you are situated and grounded, that gives rise to that knowledge, and then right there, and then it is not there, but it's in the dynamics. It's in the interaction dynamics. So that is why it's really ghostly. And then so, for example, we have this conversation, and then right here in this conversation, intelligence emerges in all of us, right? So it is like that insight emerges there, and then if we didn't have this conversation, that insight cannot be found anywhere. It is not made anywhere or available anywhere. It is made by the action itself. So that's the thing. Yeah.
That's all right. So you might have probably seen somewhat recently, that we mapped and modelled and then simulated a fly brain and put it inside a virtual fly, and then that fly was rubbing its hands and doing all the fly stuff. They weren't making it do that. Is that an example of a ghost circuit in the brain? And if so, are there any other circuits that sort of spring to mind?
Yes. So it is so you can artificially stimulate a biological system in a different way. And I mean, people try with chips implanted and then get this dormant features buried there, stimulate them, and then see what happens and with the environment. Which is maybe a good way to understand what is there. So you knock on the door and see who is inside. That's it can be an interesting way. But what we naturally have are very probabilistic networks that kicks into being when probabilistically more most probable things are in the environment, right? So the behavior of me walking on ice, maybe as let's say a South Asian, I didn't grow up in winter, right? So then the way I respond to winter might be slightly different from someone Norwegian might respond to. So but you could implant some chips on my brain and then get that behavior stimulated, maybe, but in a grotesque way, right? So, but I might learn that behavior. So, yes, and it's convoluted. Thank you.
All right. So, question.
Yes. So thank you so much, Sush, for the talk. My question is around coming back to discovering ghost circuits in nature and trying to recreate them ourselves, right? Like I really liked your point about how biomimicry, I mean, we can do our best to copy a little bit from nature, but we can't really understand what's going on. When we discover ghost circuits in nature, and when we try to recreate them, how can we design ghost circuits to, how can we predict that they will reach like a stable solution in the sense that like when you have a thing that is affecting its environment and the environment's affecting it, how do you predict whether it's reaching a stable solution? And how can you design a ghost circuit to adapt to new environments?
Yeah. So that's a big design challenge. How to design. So we use some mathematical techniques called contraction theory, and then like so, for example, it's not very complicated. Let's say like so I have a mug and I have coffee, and then I want to climb upstairs, and then like while talking to somebody, and so the ghost circuit in this present moment is I have to talk to somebody, I have to climb up the stairs, and then I have these steps with punctuated forces every time I collide, and that shakes my coffee mug, right? And then now the brain has this option of tuning my body, so it can set my elbow to a sufficiently good low pass filter. It filters out my collision forces, punctuated collision forces on the steps, and then self-stabilizes the cup rather than trying to like purposefully control the cup and then stabilize the coffee, right? So that is not how to. So like basically the design with two options. One is the ability to tune the physics of the physical embodiments, the shape and the stiffness and the viscosity, and at the same time have the physical morphological features that will self-stabilize. So with these perturbations. So as far as you have these two things, right? So like so you have the ability to control your motions and the forces with the environment, ramp it up or down, and then the ability to tune your kinematics and the stiffness in the background to assist that thing. So like that bicycle rider. Right, so the bicycle rider came off the seat and continued to ride the bicycle with bent knees, and then that is a tuning option it had. The brain used that, right, and it didn't stop riding the bicycle at the same time. So that kept. So the robots usually don't move in this space of choices. They try to be very aggressive, and then okay, I want to control everything. You cannot control, and then they fall or they break. So that's Sebastian.
Yeah, that immediately makes me think kind of what about sort of intrinsically motivated open-ended learning in robots that then attune to, if this is my outcome, can I just explore the possibility space of those parameters? But my question is sort of testing this one, design thinking is a recursive problem. Design as problem solving can be out every day, right? This can be by some version, right? It could just be, I'm a waiter and I figured out that just by holding these things here, I'm balancing all of these plates and it sort of kind of doesn't fall down. Even though you look at it and say, this is impossible. This assembly of plates here must fall down. I would argue that most of these waiters tacitly do explore design in the problem space. I don't think they have a ghost circuit in their head in terms of understanding what is going on, what's the transferable, what's the computation that's going on here, or what's that going on. So is that model just a specific model for the scientific engineering version where somebody knows the maths, and so in every day, forget about the ghost circuits because that's not what's going on in our head?
Yeah, no, definitely. So what the waiter does is this. So they first fall, and then look at the cheese. And then, the cheese stabilized. I fell apart, and then what is the problem? And then I should be like that cheese, right? And then like learn from that, and then they somehow figure out, okay, so I had to stabilize this plate, and then the solution is in tuning. And then it subconsciously learns, okay, so I will learn not about like stabilizing as a very purposeful conscious thing, as a subconscious tuning of my body and the way I walk too. So they will walk maybe with bent knees and slightly different, toe first, then the heel first strike, and then like a catwalk, and then like this tuning of and the posture, everything, right? And then the posture adjustments happening in the background. So their mastery is in the tuning. So that is why even like Bruce Lee said, like if you are a master in martial arts, you would never have to fight. Like you will never fight, really, because you will avoid it. Okay, so if a kick comes just 5 centimeters, like you move your body, the kick goes there, and you don't stay there and then like block and everything, right? So you just do that, and the kick goes away. And then his movements were very subtle, very fast, to get to the negative space of the attack. So that's all about tuning.
Satish, I have a question.
Yeah.
Something along what Sebastian asked. The world has seen many footballers, and the one that stood out to me is Diego Maradona, the boss. Yeah? So I think he's very unique. The way he plays was the kind of exchange the ball, passes the ball, and the agility. And all of a sudden, he's kind of a boat with that kind of extraordinary speed, right? Than the rest of the pack.
Yeah.
So then your presentation kind of almost made me to think that he's somehow kind of a borderland or trading with the ghost circuits by practice.
Yeah, through practice. I mean, Maradona. If you look at Maradona's moves, right? Yeah. So he always, like Bruce Lee, he is so clever to find the negative space of the rest of the pack. Yeah. Yeah. Right. So blind spot. Get to the blind spot as fast as possible, and then the common thing with these two amazing people, Bruce Lee and Maradona, are like, so they don't go with the rest of the conscious thinking. So they know the blind spots of conscious thinking at that moment, and then they somehow move to the negative space and then get the goal. Right? And then they know that the distance between the negative space and then the conscious positive space is few centimeters or few meters away.
Okay, so it helps. It does help.
It does help. Yeah.
Any final questions? Okay.
Yeah.
Yes. Sorry. Just for my own clarity to precisely define a ghost circuit.
Yeah.
Am I correct in saying that a ghost circuit requires an active role of tuning parameters as opposed to a passive? Because I'm trying to understand this idea of tuning parameters.
Yeah.
If I were to hold a coffee cup or just hold an object subconsciously, there's my understanding, and please correct me if I'm wrong, is that there's some part of my brain that's tuning the parameters in my hand to hold it and stabilize it, right? But I see that as an active role as opposed to a system passively adjusting tuning.
It's a spectrum from total passive to active, and then there's this passive layers of, basically a ghost circuit is anywhere where a bigger mechanical program is embedded in different embodiments. And when they come together, it runs as a dynamic system. So the fish body, even dead, and then the flow without any consciousness, they can come together as far as the fish evolves to be a piece of a mechanical program that can be plugged into the water flow mechanical program and then create a new mechanical program that runs in its favor. Right? So the evolutionary pressure is to create the ghost circuit. And then because you cannot change the water, you can change yourself. You can evolve to be a hack in that environment that ends up changing the way the environment responds to you in your advantage, right? Okay, that's it. So that is as far as that is there. But now you have the choice to tune yourself when you're conscious and when you're alive, and then you can continuously tune when you flow forward. Like so, rocks are different, the flow is different, and everything. Now the environmental factors, the parameters keep changing. Now we have a choice to retune yourself to re-establish that ghost circuit, right? So that ghost circuit is not a given thing. It has to be rekindled from time to time, to stay stable, right? So within stable parameters. So that's the choice of the tuning, right? Okay, so that building, for example, the Toji temple, it is there and there's no tuning. So they designed it so that like the average earthquakes they know through experience will kickstart this program in a meaningful way, right? But if there is a massive earthquake that is way beyond the design, yeah, it will collapse, right? So that's fine, like most of the cases it will survive. And then imagine you had a computer controlled new building with sensors. Yes, you have now the choice to tune, right? So let's tune the stiffness of various joints of the building and then survive any earthquake, right? So that's also fine. So the essential thing is, do you have the mechanical piece of the program that will couple with the environmental factors and then establish a new bigger circuit in favor of you, right? So that's
okay,
that's
so
yes.
that was the last question. Let's take the final one.
Yeah, I love this discussion. I mean, this is the cool thing about writing a book, right?
They got the clue. Just
yeah.
I was thinking about different length scales. So I'm thinking about like, for example, pod skaters skate on water because when you get below a certain length scale, the surface tension of the water exceeds the weight. Or even smaller, on a nanoscale, Brownian motion tends to control motion of particles and surface area to volume ratio controls various diffusion effects. How have you thought much about like how this changes with length scales going down and up, and how does this break down? Maybe if at all.
I don't know if I understood the question.
So, for example, with like Brownian motions.
Yeah, yeah.
Like if you're creating something, if you're going to use ghost circuits, say, to create some kind of dynamism.
Yeah.
But you have to be aware that like.
I see.
It's going to couple in unexpected ways, ways that seem random or seem.
Yeah. You know, it's actually so. Like if you go to nanoscale, the forces from the environment are way beyond what you can do to deflect them or control them, right? So then it goes to like perfectly, let's say random, and then go to quantum level, Heisenberg level of, it is there and it's not there. It's just like you don't know where the particle is. A particle or a wave, right? So you don't know what is what at that level. So still nature keeps order, because even at the nano level, even at a particle level, quantum level, the Gauss circuit exists in a different formation, different incarnation. That is why the particle and wave duality has it's like, let's say, a waterfall, right? So take a waterfall. So from outside, you can give a name to any waterfall from a distance, right? So let's say I can say this Devon waterfall, this is other waterfall. I can give a name by looking at it, but you zoom in to like a tiny centimeter. There's no order there. There's no order. Nothing repeats there. Right? So the way the water particles bounce off are very, very Brownian, and then quantum, like you can go to like molecular level, no order there. But like what happens is like, so there's divergence at a local level and convergence at a global level, because of the bigger gravitational force field is bigger than it supersedes or overpowers the local divergence, and then they diverge and then somehow then stay within a ball, stay within order. So the order, it is like a blanket of order and then a particles of chaos. So inside a blanket of order. So you need this, like in mathematics we say, okay, so you have to have like converging eigenvalues and then diverging things, but as far as this converging forces are bigger than those divergences, it will stay. So this is where when we think about gauge circuits. Like, so I think gauge circuits is a universal principle. So it scales from quantum to all the way to universe, large systems. So I haven't written a mathematical framework yet, so I'm developing that. So, but I think it agrees with Einstein's relativity, symmetry. It is not going to defy that. So it is at a quantum level. I don't know where I will end up, but yeah.
Just a comment to this, I mean, if you just look at the quantum systems, you would also learn about something called zero-point energy. So the zero-point energy is basically the lowest possible energy in quantum mechanical sense. That means there is no energy, but there is energy. Because it's the lowest energy that is possible, right? Okay, cool. So on the note, let's thank once again.
Thank you very much. Yeah.